In this video, we will be talking about the two types of electrochemical cells and showing a shorthand notation for describing what's going on at the anode and the cathode, and a way of representing these electrochemical cells. Electrochemistry is the study of redox reactions that produce or require an electric current. The conversion between chemical energy and electrical energy is what is carried out in an electrochemical cell. In some cases, we can input electrical energy to drive a chemical reaction, and in other cases, we can use a chemical reaction to produce electricity that we can use to do useful work. This is the case of a battery. So a battery is one in which there is a spontaneous redox reaction that takes place, and we will be calling those type of cells voltaic cells. Sometimes they are also referred to as galvanic. So a voltaic or galvanic cell is one that produces electrical energy. It's one that we can use to do useful work. Right? So batteries are voltaic cells. Non-spontaneous redox reactions can be made to occur if we add some driving force to that particular process in an electrolytic cell. These are ones in which we supply an additional amount of electrical energy to push the reaction to occur. So just as we had been talking about with the Gibbs free energy and whether a reaction is spontaneous or non-spontaneous, we have the same thing for redox reactions. So redox reactions, they do have a Gibbs free energy. We can convert that into the voltage for an electrochemical cell. And from that, we can determine how much useful energy we can get out. But in our current discussion, we will focus on more of the voltage aspect as opposed to the Gibbs free energy. Now, all electrochemical cells contain certain aspects that are the same, whether they be a voltaic or an electrolytic cell. Each contains an anode. The anode is where oxidation occurs. Both types will contain a cathode, where the reduction occurs. The electrons are going to be flowing from the anode to the cathode. There will also be a salt bridge. The salt bridge will contain some sort of a saline solution, which is a mixture of both anions and cations. The anions will be drawn towards the anode, so they will flow towards the anode. The cations will be drawn towards the cathode, so they will flow towards the cathode. At the end of most salt bridges is a semi-permeable membrane, which will allow the ions to flow through, but prevents the mixture via diffusion of the liquid that's in the salt bridge to the solution that is in your anode and in your cathode. Now, the reason why the cations are going to flow towards the cathode in these reactions is at the cathode, the electrons are flowing in, and so your cations are being reduced. A lot of times your cations in this cell are going to be plated on, not necessarily always, but often they will be plated on to the cathode. In this case, your nickel 2+ ions will become nickel solid, and so your cathode will get larger as the reaction proceeds. Because those nickel 2+ are coming out of solution, you would otherwise be left with some sort of anion-rich solution, which would mean you would be building up a negative charge at the cathode. You cannot build up a negative charge. What would happen is if you were to start building up a negative charge, the reaction would shut down. So to allow the reaction to continue to occur, you need something to replace that positive charge, which is coming off and getting plated on to the nickel electrode. And so that would be the cations in the salt bridge. So the cations in the salt bridge are used to maintain a consistent charge of the solution. So you're not building up a negative charge at the cathode, and similarly, you're not obtaining a positive charge at the anode. Now, if we look at the difference between a voltaic and an electrolytic cell, what you'll notice is they, again, all contain an anode. They both contain a cathode. There's a salt bridge between them. In this particular example, the electrolytic cell is written with the anode on the right and the cathode on the left. However, because these are physical objects, depending on which side of it you're standing on, the anode will be either left or right, and so the depiction doesn't matter as much as what's going on. For the voltaic cell, same thing. Doesn't really matter which side is the anode and which side is the cathode, though via convention, the anode is typically written on the left-hand side and the cathode is typically written on the right-hand side. The electrons will flow from the anode to the cathode. This occurs in both types of cells. You can have the same electrodes or the same half cells going on in each one of the reactions. So in this case we have zinc going to zinc 2 plus, producing 2 electrons. And in the electrolytic cell we also have zinc. The difference between them is the directionality of the reaction. So a voltaic cell is one that produces a voltage, right? You have the zinc going to zinc 2 plus and the copper 2 plus going to copper. So copper is being plated onto the cathode. So the copper side is the cathode side, the zinc is the anode side. It is producing a voltage of 1.10 volts. In an electrolytic cell, you're hooking it up to a battery that has a voltage greater than that 1.10 volt of electromotive force, and you're forcing the reaction to go in the reverse direction. So you have to overcome the drive for the reaction to go the way that it wants, which is the spontaneous direction, which is that illustrated by the voltaic cell. For an electrolytic cell, you have to provide a electromotive force that overcomes the electromotive force from the regular reaction to drive the reaction to go back in the opposite direction. It's completely possible. This is how we can get a non-spontaneous reaction to occur, by giving it extra energy to force the reaction to occur. So the difference between a voltaic and electrolytic cell, well, there's a couple differences. One is that a voltaic cell produces some useful electrical energy. Electrolytic cell requires some electrical energy to overcome the electromotive force of the regular reaction. For the voltaic cell, the reaction is going in one particular direction, and in the electrolytic cell, you have the exact same reaction, or you can have the exact same reaction, but it will be going in the opposite direction. So the voltaic cell uses the spontaneous direction of your particular setup to produce energy. The electrolytic cell will force the reaction to go in the non-spontaneous direction. So now let's focus more in on what's going on down at the atomic level. So if we take the example of a voltaic cell, your oxidation is occurring at the anode, reduction is occurring at the cathode, which is the same as what you would see with an electrolytic cell. Oxidation is at the anode, reduction is at the cathode. But if we look at the individual electrodes and see what's going on at the anode, in this case, because our oxidation reaction involves the anode here is made of zinc metal. The zinc is going into solution to forming zinc 2 plus ions, and it's releasing 2 electrons. The electrons will flow through the wire from the anode down into the cathode. So what's happening is that the zinc in the anode is coming off, going into solution, and as it does so, the electrons are moving up the electrode and moving into the wire, goes through the wire, goes down into the cathode. Those electrons then will react with your copper 2 plus, in this case, your copper 2 plus ions that are coming into contact with the cathode. So the electrons will flow in to that copper ion, causing it to plate onto the cathode. So what will happen is the cathode will grow in size in this particular reaction, but not necessarily always. In this particular reaction, the cathode will grow in size as more and more copper gets plated onto the copper electrode. Now, I keep saying that in this particular case, that the copper is getting plated on, but it doesn't have to. In some instances, you can have inert electrodes. Often, a very commonly used one is either platinum or graphite that doesn't actively participate in the reaction. Those electrodes are just used to shuttle electrons from one side to another. In those cases, you would have perhaps like copper 2 plus going to copper 1 plus. So it's staying in solution, going from the copper 2 plus to the copper 1 plus. They're both aqueous, and so the copper 1 plus is not being plated onto the electrode. In this particular case, however, of this particular reaction, your copper 2 plus is being converted into copper solid. That copper solid is plating onto the cathode. Because it would be fairly inconvenient to have to draw out an electrochemical cell diagram anytime you wanted to describe a voltaic cell, we have developed a shorthand cell notation for describing these cells, what each one of the different components are. The general format is you have your electrode followed by a vertical bar. This vertical bar will designate a phase barrier, where you're going from like a solid to a liquid, solid to aqueous, solid to gas, gas to liquid, some sort of difference between phases. Then you'll have your electrolyte. A double bar is going to indicate a salt bridge. Then you'll have your other electrolyte, a vertical bar, and then your electrode. Now, by convention, the oxidation half cell, which is where the anode occurs, will be written on the left-hand side of your cell notation. The reduction, which occurs at the cathode, so the reduction half cell is going to be written on the right-hand side. So you have your anode on the left, cathode on the right. The salt bridge, which divides the two, will be in between. And then you'll have a vertical bar to designate any phase change in your systems. Now, you can also have multiple different electrolytes in the same phase. So, for example, if your electrolyte, if the chemical reaction is going from one oxidation number to another, but both maintain being in an aqueous solution, you would designate the difference between them, or the two different components, with a comma, which will be used rather than a vertical bar. Because they are both in aqueous solution, they are in the same phase. So the vertical bars are just used to denote a change in phase, going from solid to aqueous, aqueous to gas, solid to gas, whatever it is. If it's a phase change, there is a vertical bar. If there is not a phase change, so if they are maintaining in the same phase, then the difference between them would be represented with a comma. The vertical bar is often used with inert electrodes. So a lot of times you'll have something like carbon in the form of graphite, vertical bar, your reducing agent, followed by the product of your oxidation half reaction. So let's look at a couple examples of how we can represent electrochemical cells with our cell notation. In the first example, we're going to use this setup, our zinc going to zinc 2+ as our oxidation half reaction, and our copper 2+ going to copper as our reduction half reaction. So when we're writing out our cell notation, the vertical lines represent phase boundaries, and we start with the electrode. So here, our electrode is zinc, so we would have zinc as a solid. There's a difference in phase between the electrode and the electrolyte, so there would be a vertical line. Then we have zinc 2+ aqueous as our electrolyte, so Zn 2+ aqueous. And then we have our salt bridge. So double lines indicate salt bridge. Then we have our electrolyte, which would be copper 2+ aqueous. And then we have our other component, the product of the reduction reaction, which just happens to be our electrode. So we represent that as a vertical line because there's a phase difference between the aqueous ion and the metal that is making up our cathode. So Cu, solid. So this here would be our cell notation for the cell that we have above. Now another example, let's say we have our oxidation reaction, which is zinc goes to zinc 2+, just like we had before, plus 2 electrons. But then for our for our reduction half reaction, so this is our oxidation. For our reduction half reaction, we have what we will call our standard hydrogen electrode, which is 2H+ plus 2E- goes to give H2 as a gas. Now the problem you run into here is neither the H+, the hydronium ions, nor the H2, the gas, can actually work as an electrode. This is where our reduction occurs. Okay, so we have to incorporate another wire, an inert electrode, to enable us to move the electrons into our setup. Now, the way that the standard hydrogen electrode actually looks like is here we would have maybe our wire coming over, and you would have a bell-shaped glass tube with a hose coming out. And then in the middle here, you would have your electrode coming down. You'd have your beaker around it. And inside, you got your liquid. On the electrode, you have bubbles of hydrogen gas that are forming. Right? The hydrogen gas then goes up and gets pulled out. In this case, it would be pulled out of our container. Right? So because we're going from 2 H pluses to H2, your reaction is producing hydrogen gas, and so the gas would be coming off. So you got your electrode is sitting in the acidic solution, producing some hydrogen gas, and so you have three phases. You got the aqueous phase that is interacting, so your aqueous phase, which is here, right, that touches the electrode. On the electrode, the hydrogen gas bubbles are being formed, and they're going up and being pulled out of your standard hydrogen electrode. So the way that we would represent this, saying that in essence we have the same setup, but instead of having our copper electrode here, we're working with this, our standard hydrogen electrode. So you would have zinc, which is your first electrode, right? That's your anode. Vertical line, because it is a different phase from your zinc 2 plus, aqueous, that is your electrolyte. Two lines, because you have your salt bridge. Then you have your H plus, aqueous, vertical line, H2, because there's a phase difference between the hydrogen and the hydronium ions and the hydrogen as a gas. Then you'd have a vertical line, and the metal here is often platinum. Right? And so you'd have here platinum as a solid, right? And so it would be zinc, solid, vertical line, zinc 2 plus aqueous, double vertical line, H plus aqueous, vertical line, H2 as a gas, vertical line, platinum as a solid.